So we're down to about the last 4 lectures or so in this class. I'm sure you're nearly as excited about this as I am, but I was kind of going through the stuff that Mike Wu left me, trying to figure out how to cover this stuff, which is kind of part of Chapter 5 of Casella and Berger, that neither he nor I is terribly happy with the coverage of Casella and Berger of this particular stuff. He had recommended the Goot book. I could give you a couple references as well. I will also admit that I'm a little bit confused as to whether we're even supposed to be covering this stuff in 660, because as near as I can tell, 2 years ago they didn't cover this chapter at all, either in lectures or in homeworks. And if I go to the online course description for the official university registrar, it says that like the law of large numbers and central limit theorem are supposed to be in 661. But the syllabus they gave me for 660 said it was supposed to be in 660, so honestly, I don't know what the heck's going on. But basically, the way I am planning on covering this, I mean, I think this is probably some of the most important stuff you'll get in either 660 or 661, so if you end up getting it twice, it's not a terrible thing. And a lot of it, it's like, if you're an MS student, it's important to know, but not really so important to be able to know how to do problems with. Oh, it'll probably be tested lightly in the homeworks, if at all, and likewise for the exam. If you're a PhD student, well, again, I don't know our 760 curriculum as well as we should, but this convergence stuff that we're covering today, some of these limit theorems and so on, end up being a really critical part of higher level statistical theory, so you need to know this stuff, and you'll probably have some PhD only problems on this stuff to look forward to in the final 2 homeworks. That's basically the way that I'm planning on covering Chapter 5 / these last couple lectures. So at any rate, today we're going to discuss convergence, which is sort of like the foundation for the law of large numbers and the central limit theorem. If hopefully most of you have seen this before in some form or another. If you haven't, basically what we're going to prove over the course of the next couple lectures is, first of all, the law of large numbers, often known as just like the law of averages in popular culture, which says roughly, like, if you flip a fair coin thousands, hundreds of thousands, millions of times, over the long run, the probability of heads gets closer and closer to 1/2. That if you repeat a given event over and over again, the proportion of successes approaches the probability of success. Which makes intuitive sense. We're going to prove that. The other thing that we're going to be proving is the central limit theorem, which says that if you add a bunch of stuff together under very mild conditions, it will have a normal distribution, and a very high percentage of modern statistical theory depends on this. It's possibly the most important theorem in all of statistics. So that's what we're going to do over the next little bit. Today we're going to do some foundation for these theorems and just trying to discuss when we say a random variable converges, what do we mean by that in the first place. And it turns out there's a number of different types of convergence, and I'll be describing what they mean and the implications of the different types of convergence today. So the various types of convergence that we're going to discuss is convergence and distribution, convergence and probability, almost sure convergence, convergence and LP, and complete convergence. And as I said, what this leads up to is the weak and strong law of large numbers and various central limit theorems. And the moment inequalities and the other inequalities that we discussed on Tuesday will help prove a lot of these results, which is the main reason I tortured you with all that math stuff in the first place. As I said, there's a section on it in Casella and Berger. It's not as detailed as I would like. If you have the Goot book that covers it in a bit more detail, I'm also happy to photocopy some sections from a couple of my old textbooks and post it on Sakai if anyone wants some additional information on this. So, first thing that we're going to do is define the different types of convergence. And I should start with the preface that this is another sort of thing that I took theoretical statistics a number of times, like as an undergraduate and a grad student as a course over my educational career. It was about the third time that I learned about the modes of convergence that I finally started to wrap my brain around it. So don't be alarmed if you're having trouble understanding now what's the difference between this and this initially, particularly like the difference between convergence and probability, and convergence almost surely confused me for years. And if you're an MS student, at least in my experience, this isn't something they like to nail you on in the qualifying exam. So as long as you have some vague idea of what's going on, you're probably okay. PhD students, you'll need to know this, but I think you'll get it again in 760. So if it's confusing this time, hopefully the next time it'll gel in your brain a little bit better. And I'm happy to do whatever I can to help in the meantime, and I'll try not to give too many evil problems. But as I said, 5 different types of convergence, and in the Goot book they show that if xn converges to x by any of these types of convergence, then x is unique, meaning that if xn converges to x and xn converges to y, then x and y are the same random variable. Goot will describe this in more detail, but hopefully that agrees with your intuition. Well, first type of convergence that we're going to discuss, which is the weakest type of convergence, is what's known as convergence and distribution. It's also sometimes called convergence in law or weak convergence. And the intuition behind convergence and distribution, we discussed it briefly before, it's like two random variables over time have the same distribution. It does not imply that the sequence of random variables converges to the value of the other random variable for with any frequency whatsoever. It just means they have the same distribution. Like, for instance, say random variable 1 is I flip a fair coin, and I flip a fair coin that's heads with probability 1/2, count number of heads. My sequence of random variables is, say I flip a sequence of coins, and the probability of heads for this sequence of coins, they're all weighted just slightly. The probability of heads for this sequence is 1/2 plus 1 over n, something like that. So obviously, as n gets larger, the second coin, the probability of heads gets closer and closer to 1/2, so it'll converge to the same distribution as the first coin. But the two coins do not have to have the same value, either heads or tails, for any of the possible events. All we know is that they have the same distribution, that the probability of 1 is 1/2, and the probability of 0 is 1/2. That's the intuition behind that. The main area where we care about convergence and distribution is the central limit theorem, that you add a bunch of stuff together, it converges to a normal distribution, but again, it's convergence and distribution. If I take, like, the average number of people who voted for Barack Obama in the last election, that will have a normal distribution for a sufficiently large sample size. If I look at the number of people who think that Fruit Loops are a good breakfast cereal, that will have a normal distribution for a large sample size. There will be no association whatsoever between these two random variables, other than that they both have a bell-shaped curve. So that's convergence and distribution. And the formal mathematical definition is that if xn converges to x in distribution, then the limit as n goes to infinity of the CDF converges to the CDF of the final variable x at all continuity points of x. And as you'll recall, CDFs can have at most a countable number of discontinuities. The 690 students got to prove that in their homework a while back. And you can also prove, but I won't, that if xn converges to x in distribution, then for any bounded continuous function, the expected value of x of n of g of x of n converges to the expected value of g of x. Well, the next two types of probability of convergence that we will discuss are convergence and probability and convergence almost surely. And these are much stronger than convergence and distribution because, as I said, convergence and distribution, all it means they have the same distribution. It does not mean that they will necessarily have the same value. Convergence and probability, it means that basically the probability of the possible outcomes for which xn differs by more than epsilon from x is going to 1 for n as n goes to infinity for any possible value of epsilon. It's basically saying that, I'm trying to think of a simple example of this one and not succeeding very well, that maybe, like, for instance, you have a coin that you can stick something on one side of it to weight the coin so that the probability of heads increases, and you flip it. Well, that's a bad example because there's no way to flip it under exactly the same circumstance. Well, I can't think of a good example of this off the top of my head. I should have thought of one before I came to class, but if it does imply that for all the possible outcomes, the probability of the outcomes for which the sequence of variables xn differs by more than epsilon from x is going to 0. Or equivalently, the probability that it's more than epsilon away from x is going to 0. Convergence almost surely is very similar to convergence and probability, and as I said, it took me a long time to understand the difference between the two. The convergence almost surely means that the set of outcomes where x of n converges to x has probability 1. And what does that mean? How is that different from convergence and probability? Well, the simplest way that I can think of this is with a coin tossing example again. And like I said, if your head still hurts trying to figure out the difference between these two, don't worry, because it took me a very long time thinking about this before I really understood it. But the basic idea is, like I said, we have strong the laws of large numbers says if you flip a coin a large number of times, the proportion of heads goes to approximately 1/2. And over the course of the next few lectures, we're going to discuss the weak law of large numbers and the strong law of large numbers, where the weak law of large numbers says that it converges in probability to the proportion of heads converges in probability to 1/2, and the strong law of large numbers says it converges almost surely to 1/2. So what the heck is the difference? Well, the weak law of large numbers is saying that as n goes to infinity, the probability of all sequence of tosses such that it's more than epsilon away from 1/2 is going to 0, but it says nothing about any one particular sequence of tosses. That if I flip a coin an infinite number of times, not every possible sequence converges to 1/2. I could, in theory, flip a coin heads an infinite number of times consecutively. Probability of that event is 0, but it's a possible event, and obviously if I flip heads every single time, that's not converging to 1/2. And similarly, if I flip tails an infinite number of times, it would not converge to 1/2. There's others like that. If I got a sequence of 5 heads plus a tail, then 5 heads plus a tail, 5 heads plus a tail, that's not going to 1/2 either. There's a bunch of outcomes where it doesn't converge to 1/2, but what the weak law of large numbers tells us is that the probability of all these possible sequences of outcomes that don't converge to 1/2 are all 0. That, I know this is kind of confusing because if you're a PhD student, you've encountered this before, but just because something has probability 0 doesn't mean it cannot happen when you're dealing with these types of continuous outcome spaces. But the probability of all these events such they don't converge to 1/2 is 0. With probability 1, you will get a sequence of events that converges to 1/2. So questions already.
But isn't the probability of the sequence of converging to 1/2, like each one of their sequences is also 0?
Yes. But the basic idea, I mean, if you've done the 690 homework, it'll make a little bit more sense, is that using measure theory, you can try to come up with smart ways of trying to define the probability of all sets of sequences, and you can show that the sum of the probabilities of all of the events that do converge to 1/2 is 1.
So the coin flip example is almost surely not improbable.
Well, it's both probability and almost surely. Right now I'm explaining improbability to try to explain the difference between the two. So in probability it says there's all these different sequences of events, uncountably many in fact, but the probability of all the sequences of coin tosses that converge to 1/2 is 1. It's possible to get a sequence that doesn't converge to 1/2, but the probability that happens is 0. However, it says nothing whatsoever about any particular sequence of coin tosses. That you're given that the sum of the probabilities of all the sequences that converge to 1/2 is 1, but if I'm flipping my coin an infinite number of times, under the weak law of strong numbers, it's possible that I could get to within epsilon of 1/2, then I get an unlucky streak, so I go more than epsilon away from 1/2, and then I get close to 1/2 again, and then I get far away again, then get close, that an infinite number of times that I move in and out of that epsilon band around 1/2. That is possible under the weak law of strong numbers, or convergence and probability. Convergence almost surely says that cannot happen. That every single sequence of coin tosses that goes to 1/2 is converging to 1/2, just like the idea of limits from calculus, that it says there exists some n such that when you go past that n, you're within epsilon of 1/2 for forever. So that's the basic idea of the difference between the two. I'm going to give another example here in a second that might hopefully make it somewhat clearer. If it still makes no sense, then just think about it for the next year and a half, and then hopefully it'll make sense, because that's about how long it took for me. But, because convergence almost surely is weird as well, because obviously the statement I just made isn't quite true, because there are sequences that never go within epsilon of 1/2. I could flip heads an infinite number of times, for instance. But the set of sequences that do not go within epsilon of 1/2 has probability 0. That in particular, the sequences that I described earlier that go like within epsilon of 1/2, then more than epsilon away, then go within epsilon of 1/2 again, go more than epsilon away, and so forth, those also have probability 0 under almost sure convergence.
So the difference that's for almost surely after some n, the probability of all ones that are in 1/2 is 0, whereas in probability after some n, the sum of all ones that are in 1/2 is less than epsilon, like the sum of their probabilities, or?
Yeah, I mean, I'll give another example of this later on. I mean, what might help to understand it is you have to remember that a random variable is just a function from the outcome space to the real line. And almost sure convergence is basically just pointwise convergence of this sequence of functions. Convergence and probability says that the probability or the measure of the points where it doesn't converge to the limit function is getting smaller and smaller, but it doesn't say anything about a point-wise convergence at any particular point. But I'm going to give approximately this example later on, but maybe I'll just quickly sketch this on the board so that you can at least be thinking about it. But say my original outcome space is the set of real numbers from 0 to 1. So my random variable in this case would just be a sequence of functions from 0 to 1 to the real line. And say I defined a sequence of functions such that the first function is just like y equals 1, for instance. Then the second one, I split it in half. And so that's the first piece, that's the second piece. Then I split it into quarters and make it twice as high, etc., etc. So I have a sequence of functions. Maybe I should draw these one at a time. The first function looks like that. The second function looks like this. The third function looks like that. Fourth one is even taller and skinnier, etc., etc. That this sequence of functions is converging to 0 in probability because you can see as the sequence of functions increases, the set of points that is not equal to 0 is going to 0. For the first function, for the first function in the sequence, none of the points are equal to 0. For this function, the probability of being 0 is 1/2. If it's between 1/2 and 1, here it's 1/2 again. Here, the probability of being 0 is 3/4. You go down the sequence, the probability of the functions equal to 0 is 1/8, 1/16, 1/32, etc. The probability that the function is not equal to 0 is getting smaller and smaller. However, it does not converge point-wise to 0 at any particular point because there will be an infinite number of times where it's more than epsilon greater than 0. This would be an example of something that converges in probability but does not converge almost surely. Convergence almost surely is just saying it converges point-wise to 0, except on a set of measure 0, basically.
You just said there'll be an infinite number of cases where it's more than epsilon?
Yeah.
Oh, but the probability of those will be less than epsilon for some past some.
Yeah. That, like I say, say I choose 0.1 here or something, there will be an infinite number of times where the value of f of 0.1 is some large number. So you can never find some n such that when you go past that n, you're within epsilon of 0. This sequence of functions does not converge point-wise to 0 anywhere, but the probability or the measure of the points where the function is not equal to 0 is going to 0. And like I say, I apologize for the fact that it's confusing. Half the reason I teach it is so that you can spend the next year thinking about it and maybe hopefully understand it the next time you see it. But I'm going to give that example a bit more explicitly later on. But as I said before, convergence and distribution is the weakest form of convergence and does not imply the other forms of convergence. One exception is the following special case, that if xn converges to x, where x is a degenerate distribution, that is, the probability that x equals a is equal to 1, then if xn converges to x in distribution, then xn converges to x in probability as well. Again, a coin tossing example is the easiest way to see this, that if you flip a coin a bunch of times and count the proportion of heads, as I said before, that will be converging in distribution to 1/2. This theorem says that that's also converging to 1/2 in probability because it's converging to a random variable that's just a constant that takes a single value with probability 1. So the proof of this is that say that xn is converging to x in distribution where x is equal to a with probability 1. Well, then the probability that xn, absolute value of xn minus a is less than epsilon is just equal to the probability f sub x of n evaluated a plus epsilon minus the CDF evaluated at a minus epsilon. And so if you take the limit of both sides, since by definition of convergence and distribution, the limit of the CDFs goes to the CDF of f of x at all continuity points of f of x n, so that just converges to f of a plus epsilon minus f of a minus epsilon, which of course for a function that has the degenerate distribution at a, that means the CDF is equal to 0 for x less than a and is equal to 1 for x greater than a. So f of a plus epsilon minus f of a minus epsilon is just 1 minus 0, which is equal to 1. So that proves that it also converges in probability to x. And like I said, the distinction between almost sure convergence and convergence in probability is pretty subtle. That don't worry about it if it doesn't make perfect sense right now. And we'll show how you can use Markov inequality and Chebyshev's inequality to establish convergence and probability. Establishing convergence almost surely tends to be much hairier in general. And almost sure convergence is stronger than convergence and probability. If xn converges to x almost surely, then it also converges to x in probability, but the converse is not true. That's the example that I just showed on the board. It's possible for something to converge in probability to something else, but not almost surely. Other types of convergence, there's convergence in the arith mean, which means that, first of all, that the arith moment of the sequence of random variables exists for all n, and the limit of the expected value of xn minus x to the power r is equal to 0. And this is sometimes called convergence in LR or convergence in the LR norm. Some books, particularly functional analysis books, tend to use LP. I don't know if anyone in here has ever taken functional analysis. You don't really need it as a statistician, but you'll spend a lot of time learning about LP spaces if you do. And convergence in the arith mean is basically equivalent, well, it is completely equivalent to convergence in LP. My recollection is I don't remember using this a whole lot in statistics. It seems like it's in the functional analysis world where it's more likely to come in handy. It's usually these first three types of convergence that I just discussed that get used in statistics because you need it for the various laws of large numbers plus the central limit theorem. And the last idea that we'll discuss briefly is what's known as complete convergence, that it's defined in Goot as you just find the probability that xn minus x is greater than epsilon for all n and sum it up, and if that's finite for all epsilon, then you have complete convergence. And the reason you care about this typically is because it's slightly stronger than almost sure convergence in that if you have complete convergence, you get almost sure convergence as well. You can find a few counterexamples where the converse isn't true, but they're weird. They're not things that you're likely to encounter in day-to-day practice. And the main advantage to complete convergence, if you're trying to prove that something converges almost surely, that can be a big pain in the butt, but oftentimes it's much easier to prove that something has complete convergence, and if you get complete convergence, that implies almost sure convergence. Yeah, I guess I basically just said that. In fact, some books use this as the definition of almost sure convergence, or at least that's what it said in these slides. I've never actually seen one of these books. But the main advantage to using this is it gives you a relatively easy way to prove almost sure convergence. So, a couple examples of these different types of convergence that, say, for instance, you have a sequence of random variables xn, each of which has a gamma and n distribution. Well, then xn converges to 1 in probability. How do we prove this? Well, the expected value of xn is 1, and the variance of xn is 1 over n. So we can apply Chebyshev's inequality to show that the probability that xn minus 1 is greater than epsilon is less than or equal to 1 over n epsilon squared for all n. Therefore, for any value of epsilon, as n gets large, that's going to 0, ergo xn converges to 1 in probability. So, as I said, that's the reason that I spend all this time proving these inequalities and shoving Chebyshev's inequality and all this other stuff down your throats, is because you can prove things like this. In fact, this basically the same argument is what you do to prove the weak law of large numbers, as you'll see here in a second. So, second example, say you have binomial xn, the xn is binomial with number of trials n and probability of success lambda over n, then xn converges in distribution to x, where x has a Poisson lambda distribution. I won't go through all the ugly details of this proof because I've done it before, but what it basically boils down to is if you take the limit of the left-hand side of this thing as n goes to infinity, you end up with something that's e to the minus lambda times lambda to the y over y factorial. And the right-hand side is, of course, just the distribution function of Poisson with parameter lambda. So that proves that xn converges to x in distribution. You can also prove convergence in distribution by looking at the convergence of the moment-generating functions or characteristic function, as we talked about earlier. And in practice, that's usually what you do, actually. That the single most important example of this, as we'll see in a couple lectures, is that the central limit theorem, you can prove that under very mild conditions, the characteristic functions of almost anything will converge, once you add it together, will converge to the characteristic function of a normal distribution, ergo the central limit theorem. Okay, so now back to this weird example that I just tried to draw on the board. That what I'm saying here is just basically trying to say a fancy math way of writing this, that for each positive integer n, you can find a unique k in m such that n equals 2 to the k plus m. If it's not as complicated as it sounds, that say like 3 is equal to 2 to the 1 plus 1, then 4 is just 2 squared, obviously. 5 is 2 squared plus 1, 6 is 2 squared plus 2, 7 is 2 squared plus 3, then you end up with 2 to the third, of course. You can write every unique integer like that. And from there, you can go to a function that says, let xn of omega, remember omega is just defined on 0, 1 here, be equal to 2 to the k if m over 2 to the k is less than omega less than or equal to m plus 1 over 2 to the k, 0 otherwise. That's basically the sequence of functions that I just wrote up here. That the first function in this sequence is just y equals 1 on the interval 0 to 1. The second function is y equals 2 on the interval 0 to 1 half and 0 otherwise. The third function is y equals 2 on the interval 1 half to 1 and 0 otherwise. Then it's y equals 4 on the interval 0 to 1 fourth, etc. And just go through that an infinite number of times. Then it's pretty easy, and that's a typo, that should be 1 minus 1 over 2 to the n, and probability xn equals 1 over 2 to the n. I'll try to remember to fix that and post updated slides, but it doesn't matter that much. The point is the probability that xn is equal to 1 is going to 1, and the probability that xn equals, oh, double typo there, the probability that xn equals 2 to the n is going to 0. So you choose any epsilon smaller than 1, and the probability that xn greater than epsilon is going to 0. So xn is going to 1 in probability, but for any given point between 0 and 1, the limit as n goes to infinity of xn evaluated at that point does not exist, because there'll be an infinite number of times that xn of 0.1 or xn of 0.7 or xn of square root of pi over 17, whatever number you choose, there will be an infinite number of times where it's greater than, where it'll be greater than epsilon. So this sequence of functions does not converge to, oh, there's a million typos on this slide, does not converge to 0 point-wise for any point in that interval, so it does not converge almost surely. And I apologize for putting a million typos into what's already one of the most confusing slides in this lecture, because I'm sure that makes it much easier to understand. I'll try to clean this up tonight. Well, just to try to cast some further darkness on the subject, let's take a similar sequence of random variables. We say the probability that xn equals 1 is 1 minus 1 over n squared, and the probability that it's equal to n is 1 over n squared. Well, for sufficiently small epsilon, that implies that the probability that xn minus 1 is greater than epsilon is just equal to the sum from n equals 1 to infinity of 1 over n squared. And if you remember from advanced calculus, that sequences converges for k greater than 1, in particular for k equals 2. So, which tells us that xn goes to x with incomplete convergence with x equals 1. So we've also proven that xn converges to 1 almost surely in this case. That trying to prove the point-wise convergence of all the points in that outcome space, I mean, I'm not sure how you would even do that in this example, but it's fairly easy to show complete convergence in this case, which then implies almost sure convergence. So here is how the different types of relationships, the different types of convergence relate to one another. That complete convergence implies almost sure convergence, which implies convergence in probability and convergence in distribution. And convergence in the rth mean for any possible value of r implies convergence in probability. But convergence in the rth mean and convergence almost surely / complete convergence don't tell you anything about each other. You can have something that converges almost surely but does not converge in the rth mean and vice versa. that dumb mnemonic, remember this, is all probabilist string to say almost sure convergence implies convergence and probability implies convergence and distribution, but not the other way around. And you can also show that for convergence in the rth mean, if r is greater than or equal to s greater than or equal to 1, then convergence in the rth mean implies convergence in the sth mean. It's hard to say s. That if you show the convergence in the rth mean for any possible value of r, then you've also proven convergence in the rth mean for any possible value of r less than r. And I will prove real quickly that convergence in probability implies convergence in distribution, because it's kind of an informative proof for how you would prove this type of thing. So let's choose some epsilon greater than 0 and look at the f's. Remember, to prove convergence and distribution, we need to prove that the CDF of xn converges to the CDF of x at all continuity points of these CDFs. So let's just take the CDF of xn evaluated at some arbitrary point x. Well, that's of course just equal to the probability that xn is less than or equal to x. And that is of course equal to the probability that xn is less than or equal to x, and x is within epsilon of, or xn is within epsilon of x, plus the probability xn is less than or equal to x, and xn is greater, and xn is greater than epsilon from x, blah. And that is less than or equal to the probability that x is less than or equal to x plus epsilon, plus the probability xn minus x is greater than epsilon. Well, why is that true? Well, the second piece is fairly obvious, that the event xn less than or equal to x and xn minus x greater than epsilon is a subset of the event probability xn minus x is greater than epsilon. So the probability of this event here has to be greater than or equal to the probability of this event here, because the event up there is a subset of the one down there. The left-hand piece is a little less obvious. Why is that true? Well, the event that x minus xn is less than or equal to epsilon is the set of values for which minus epsilon is less than or equal to x minus xn, which is less than or equal to epsilon, which is a subset of the values for which x minus xn is less than or equal to epsilon, which of course equal to values that x is less than or equal to xn plus epsilon. And the event xn is less than or equal to x, and x is and the event that xn is less than or equal to x, the first part of this event up here, and this event here, that's a subset of the first event, x less than or equal to xn plus epsilon, is of course just a subset of the event that x is less than or equal to x plus epsilon. So the grand take-home message is this event here, x less than or equal to x plus epsilon, is a subset of this event, or other way around rather. This event here is a subset of this event down here. Where does my pointer go? It's a subset of this event down here. So the probability of this event on the top row is less than or equal to the probability of that event there. Oh. And that's just the first page of the proof. But anyway, so that gives us that f of xn evaluated at x is less than or equal to the CDF of x evaluated at x plus epsilon plus the probability that x minus xn is greater than epsilon. So as n goes to infinity, that gives us that we know that the probability that x minus xn greater than epsilon is going to 0 because we're assuming convergence and probability. The limit on the left-hand side, we don't know if it necessarily exists. For some x's it may not, but we do know that for every possible n, that inequality is satisfied, so the lim sup, which definitely does exist, will be less than f sub x evaluated at x plus epsilon. And if we reverse the roles of xn and x in the above equation, we get f sub x of x is less than or equal to f of xn evaluated at x plus epsilon plus this probability that xn minus x is greater than epsilon. Once again, this last piece is going to 0, and we can replace x with x minus epsilon, and we get f sub x of x minus epsilon is less than or equal to f sub xn evaluated at x plus the probability of that last piece, and rearrange the terms, we get the f sub x evaluated x minus epsilon minus this probability of xn minus x greater than epsilon is less than or equal to f sub xn of x. So again, taking the limit of both sides, the limit of the right-hand side doesn't necessarily exist, but the lim imp of that sequence does exist, and it's greater than or equal to the CDF of x evaluated at x minus epsilon. So now we combine those two pieces together. We get that f sub x of x minus epsilon is less than or equal to the lim imp of this sequence of CDFs, less than or equal to lim sup. This sequence of CDFs is less than or equal to f of x plus epsilon for any epsilon greater than 0. And that, of course, says that if f sub x is continuous, then for small epsilon, f of x plus epsilon is converging to f sub x minus epsilon as epsilon goes to 0, implying that the lim imp and the lim sup are converging to a common limit, and that which is equal to f sub x at x. So we get that the limit of the CDFs is converging pointwise to f sub x of x. And yeah, don't worry if you didn't immediately grasp all the details of this proof. That's definitely not going to be on the final or anything. It is worth reviewing to make sure you understand it if you're thinking of taking 760 someday, because this is the type of logic that you will have to use to prove things in that class. If f sub x is not continuous at x, then all we get is that the limit from the left of f sub x at x is less than or equal to, and great, another type. Well, I guess that's not a typo, because the limit on the right, the CDFs are always right, continuous, so the limit of f sub x at x as it goes to x from the right is just equal to f sub x of x, but on the left-hand side, that's not necessarily the case, and all we can say is that that limit from the left is less than or equal to the limit of the sequence of CDFs less than or equal to the lim sup of the limit of the sequence of CDFs less than or equal to the CDF evaluated at x. And you can also prove fairly easily that if xn converges to x in the rth mean, then it converges in probability to x. That inequality, that theorem is much less painful to prove. That by Markov's inequality, the probability xn minus x is greater than epsilon is equal to the probability that xn minus x to the rth power is greater than epsilon to the r, by Markov's inequality is less than or equal to the expected value of xn minus x to the rth power divided by epsilon to the r. If it converges in the rth mean, then the numerator is going to 0, so the whole thing is going to 0. So, in particular, a very important example of this, let's say that you have y1 up to yn, BIID with common mean mu and variance sigma squared. Let's let y bar be the average of these things. Then the expected value of y bar minus mu squared is, of course, just equal to the variance of y bar, which can easily be shown to be sigma squared over n. Well, that's going to 0 as n goes to infinity. So, since yn, or y bar sub n converges to mu in the second mean, that means that yn converges in probability to mu, meaning that for large values of n, the probability that this mean is more than epsilon away from mu is going to 0. So, in other words, we have just proven our first form of the law of large numbers, saying that if you have a bunch of IID things with common mean mu and common variance sigma squared, the probability that the mean is more than epsilon that the sample mean is more than epsilon away from the population mean is going to 0. Hooray, we're done with this class. Well, not quite. Then we still need to prove the central limit theorem, and we'll also see that you can prove the various laws of large numbers under weaker conditions than this. I need to double check my notes. I hope I'm not telling you lies here, but my recollection is that you can prove this even if the variance doesn't exist. That I think this is true even if only the first moment exists. But come back, well, not Tuesday, because Tuesday will be review session for the exam. Come back a week from Tuesday, and I'll tell you more about it. Anyway, any questions on anything today? I apologize for the fact that this is a little bit obtuse.
So complete convergence doesn't tell you anything about convergence in arithmetic?
Right. Oh, whoops. I think I hit the thing. Oh, wow. Lecture's over anyway. Yeah.
Quick question. I'll come talk to you in office hours about